Hey everyone, welcome to the second talk of the day. After Dim's amazing keynote, we will be taking you through a journey to the internals of the Kubernetes API. I am Navarun.
And I'm Nikita.
The Kubernetes API server lies at the center stage of all components. Each component of a Kubernetes cluster, for example, the scheduler, kubelet, kube controller manager, all talk to the Kubernetes API server for operating on objects, be it creating them, reading them, updating them, or deleting them. The API server reads, manipulates state, and then stores it to etcd. API groups in Kubernetes are logical collections of related functionality. For example, workload objects like deployment, stateful set, replica set are in the apps group. There are about 20 plus API groups in the Kubernetes API ranges. When we see the API endpoints, we will see that the core group is a bit special. We will see that later when we discuss about resources. Going ahead, the Kubernetes APIs are versioned, and each API group can have one or more versions. They're usually of the form v1 alpha 1, then v1 alpha 2, then if it graduates to beta, it's v1 beta 1, and so on, eventually going up to v1 v2. The core group at this point in time has only a single version, but groups like apps has versions like v1 beta 1, v1 beta 2, and v1. Any group can have more than one or just one API versions. When present in multiple versions, Kubernetes API server needs to perform conversion between them such that there is no loss of data. Now you have to keep in mind that versioned objects are just different representations of the same stored object. Types in Kubernetes API usually graduate from alpha to beta to general availability, with alpha being the most volatile, as in they can change during the life cycle, beta being closer to stable, and general availability means they will be there for certain number of releases unless a deprecation has been called on. Next up, kind is the type of an object in the Kubernetes API universe. And you might have seen like each object that is returned by the Kubernetes API has a field called kind. Pod, deployment, stateful set, service are examples of kind. Each of these kinds exist in a versioned API group. This very relationship is called a group version kind, or GVK. We will use this abbreviation a lot in future slides. Now you might wonder, how are these Go types, which we define in code, mapped to group version kind? We will look at something called a scheme. Scheme maps Go types to all possible group version kind combinations. Scheme also stores a list of conversion and defaulting functions. We will explain what converters and defaulters are in a later part of this talk. In the Kubernetes world, there is also a concept called resource. A resource identifies an HTTP endpoint exposing the CRUD semantics of the associated object. Remember I told that each of these APIs returns you a representation of the object that you are accessing, which is stored on etcd. A resource is always part of a versioned API group other than a few special endpoints, them being HELZ, REDZ, which are mostly used for cluster administration. And basically this combination of a group, version, and a resource is used to identify an HTTP endpoint. And each of these endpoints receive and return in unique kind. For example, if I do get/deployments, as in the first example, the API server will return a deployment list object. If I get on a specific deployment, it will return a deployment object. Similar case with the later example. Coming to the later example, you notice that the structure is a bit different for core group types. This is a really special case. In that case, we use the /API prefix, and in case of all other API groups, we use /APIs. There is also something called a subresource. Some of these resources may have a subresource like port forward, exec, logs, which are used in case of pods. In case of resources which can be scaled, there is a subresource called scale, which is used by the horizontal pod autoscaler. The mapping of a GVK to a GVR is called REST mapping, and there are helpers called REST mapper which perform the same, which gives the users the flexibility to map between these two concepts. A GVK is essentially served by the API server under GVR HTTP endpoints that we saw previously. Do note that a GVK can map to many group version resources. Most of the GVKs map to a single GVR, but objects like scale can exist in multiple GVRs because by virtue of them, they can be present in others. External types are what you see in the staging src-catus.io/API directory. In the Kubernetes code base, you may check out the code base from github.com/Kubernetes/Kubernetes. These external types are what are supposed to be consumed by the users, and these are externally consumable. Now, coming to internal types, they are also known as hub types, and they are not exposed to the users. It is not a good practice to use them as a dependency in your code. They are reserved for usage internally in the API server. Now, this internal types give the code base flexibility to version objects by the consumers as external types, but then at the same time provide a baseline for internal computation as hub types. For objects having multiple versions, the internal types acts as a conversion medium. Now, having told you about the concepts that are used in the Kubernetes API server, we will dive into the code base, and we will be using here a VS Code extension called Code Tour, and you can go to the gist and download the JSON file to essentially replay the Code Tour on your own computer. Now let's deep dive into the code. So number one thing. So if you have checked out the Kubernetes code base, you can see that inside the staging src-catus.io/API directory, you can find all of the external types which can be imported by the users. The external types directory holds all of the API groups. As we can see here, we have apps, authentication, authorization, autoscaling, batch, certificates. These are all the API groups in the Kubernetes API. Now, inside all of these directories, we have API versions. Inside that, inside those apps v1 directories, basically the versioned API directories, you will find a types.go, which contains all the kinds that are present in this specific group version combination. Now, all of these external types have tags to generate some repetitive code, OpenAPI spec, and code documentation. Along with types.go, there is a register.go inside each versioned API group directory, which contains helpers for registering a type GVK mapping in what is called a scheme. You can see in register.go, there is a helper function called addNownTypes, which essentially calls scheme.addNownTypes and provides it with a list of all kinds that you want to register for that group version. Here we are passing in the group name, apps, and a version called v1. Hopping onto internal types, the pkg/APIs directory in the Kubernetes code base has all the internal types. For example, we saw deployment as an external type. Here we see deployment as an internal type. Notice that there are no JSON or proto tags to annotate this code because all of those repetitive stuff is generated from the external types. We do register the internal types as well, but they are registered with a special internal API version constant, and these types are not considered stable or serialized. The install function in pkg APIs apps install.go registers the external and internal API types to the scheme whenever this package is initialized. So you can see here that we are registering our internal types. We're registering all of our version external types. Now, we have talked a lot about scheme. We have seen some preview about scheme. Now, you can see here that scheme stores information to map between the registered Go types and the corresponding GVKs. It also stores any conversion functions and defaulter functions. There are information in the structure to give you all of the information when you have a GVK and you want to find the code type for the same. Now that we understand like how these API types are registered into the runtime scheme, we have to understand like how an API request is handled. So whenever an API request comes to the API server, they go through a set of filters, which are defined in default build handler chain in a file called config.go in the pkg server directory in the staged API server. Now, these filters in sequence run some checks, and if any of these checks fail, an appropriate HTTP return code gets generated, response code gets generated along with an error message. And if any checks, if all the checks succeed, it goes on to the next step. We will see in the next part of our talk. The chain has filters for panic recovery, API priority and fairness, authentication, authorization. It also has filters for adding course headers. There are things for auditing. So now, when the request passes through all of them, we have to see like which logic gets called. Now we have to understand like how is the multiplexer structured. So depending on the HTTP path of the request, we have some rules which will request to the appropriate handler. Now, where are these defined? So when you instantiate or set up an API server process, it gets cascadingly installed using an install rest method, which basically checks the storage in your runtime. And based on that, it enumerates through all the API groups and installs the corresponding endpoints, which map to each of those GVKs, which are exposed in the current Kubernetes version. Now, with this, we have completed part one of this session. I will hand it over to Nikita, who will give you a overview of conversion, defaulting, and how we handle the process of admission and mutation. And I'm going to remove myself and then continue giving a pause or something.
Thanks, Navaran, for the wonderful code-based walkthrough. Now that we have seen how the Kubernetes handler chain works, let's understand how resources are serialized and persisted in etcd. And the most important concept to understand about serialization in Kubernetes is this thing called conversion. So what are we talking about? What are we converting? So the first thing to understand about conversion is that each API resource has something called as a storage API version. What is a storage API version? Each resource needs to be stored somewhere. So it's stored in etcd, but what version is it stored in? So this version that it's stored in is called the storage API version. And it is usually the most newest and stable version. Let's take an example by considering the storage version to be v1. If you write a YAML file or if you create a resource using kubectl apply and you specify the API version as v1 beta 1 in your YAML file, then this v1 beta 1 version would be called the input version. Your input version could be even something like v1 beta 2 or v1 beta 3. And in all of these cases, since v1 is the version of the resource that will be stored in etcd, we will need to convert them to v1. But since this means that there could be several of such cases of conversion, because v1 beta 2 to v1, v1 beta 3 to v1, beta 1 to v1, to make it easier, Kubernetes uses something called as an internal version, or it's also called a hub version. This is equivalent to the internal and external types that Navaran was talking about. Similarly, v1 beta 2 would be converted to v1 via the internal version, and the same goes for v1 beta 3. Let's just consider v1 beta 1 in our subsequent examples to keep things simple. Another important thing to understand here is that the process of moving from v1 beta 1 to internal and so on also involves something called defaulting. For example, what if there are additional fields in v1 that are not present in v1 beta 1? So how would we ensure that these additional fields are defaulted or present in v1 when we convert the object? To ensure that the v1 version object eventually contains valid fields, defaulting is done. That is, fields are defaulted, whichever ones are desired, after the conversion. So please remember, like whenever we're usually talking about conversion, we're also talking about defaulting. So now that we're familiar with conversion, let's understand how the overall resource handling works. So the first conversion that we talked about was the input version to the hub version. So for the first conversion from v1 beta 1 to the internal version, this process is called decoding. And now decoding involves three things. First is called the serialization, or basically you submit a YAML or a JSON data. So you convert this data from YAML form to the Golang type. And second is called defaulting, that it applies the default values that we talked about. And finally, the third step is conversion to the internal version. So just to recap a little bit, serialization, convert the data in the Golang form, apply the default values, and finally convert it to the internal version. So we have the internal version and we want to convert it to the storage version. This process also undergoes three steps. So the first step is admission. So if you, where mutating and validating webhooks are applied. And if you're not familiar with webhooks or admission, you can think of them as like mutating webhooks can modify the object and validating webhooks can reject a request. So first step is admission. The second step involves this construct called as a registry. What it basically means, it prepares the object for getting stored into etcd by doing some additional operations on top of it, like removing the status part. So if you've noticed, whenever you create an object and if you specify the status, it doesn't get persisted in etcd. Why? Because the status part is removed here in the registry. Validation is also done here. So like the name is a valid, like follows the proper characters. It's not a there are specific constraints that we use in Kubernetes. All of those validations are done over here. And in the third step, finally, the object is encoded before it can be stored in etcd. Remember that we talked about this thing called as a storage version. So encoding here means conversion to the storage version, applying the defaults and deserializing it into protobuf or whatever the specific storage media type that's been provided. And finally, the object gets stored in the v1 version in etcd. So to recap very quickly, so you have the internal version and the storage version, and the conversion between them takes place in three steps. So first you have admission, so mutating and validating webhooks. There's this thing called as a registry, which we will look in the code what it exactly means. And it does things, it does some operations before creation, and it also does validation. And finally, it gets converted to the storage version before it gets persisted to etcd. Let's quickly look through the code and what it looks like. Like Nabarun, I will also be using the VS Code extension code through Code Tour. And if you want to run the Code Tour in your VS Code, you can do that by using the gist in the slide. Let's quickly walk through what the code actually looks like. Don't worry, even though this looks scary and the API server code feels like it could be scary, it really follows some basic principles that we just saw. So I'm going to start the code right now. So the first thing we're going to be looking at is the API server directory. It's in the, if you go to the Kubernetes GitHub source code, it's in the stagings src or source gates.io API server directory. And in specific, today over here, we're going to look at REST handlers. So what we're going to do is we're going to look at the workflow for creating a resource. And the REST handlers or the creating handlers are specified in the handlers directory. So before we look at how a request, like a resource gets created, let's look at what happens when you actually send a request to the API server. When you send a request, there's this thing called a request scope, which contains common fields that are required for all these handlers. So it contains conversion, defaulting, and such methods. For instance, this field is called a serializer or a negotiated serializer. It's basically an interface for obtaining encoders and decoders for multiple media supported types. For instance, if you specify a JSON format or if you specify YAML format, both of them have separate encoders and decoders, but all of them can be combined together in this thing called a negotiated serializer. Next, you have this thing called as an object converter, which is used for conversion. So converting one objects from one version to another. So from v1 to the internal version. And then you have a defaulter which does defaulting. Now let's look at how a resource actually gets created. So there's this function in the API server package called, so there's this file called create.go, and then you have this function called create named resource. So like the command says, it will handle a resource creation with a name. So it just creates a resource with a name. Now, create named resource basically it just calls create handler. So the main fun is in the create handler function, and we will look at how that's done. So let's look at what create handler does. Create handler, firstly, you're creating a named resource. So first you want the name and the namespace of the resource that you're creating. So that is derived from the request. Then serialization needs to occur. Remember that we talked about first you had that v1 beta 1 resource and it had to be converted to the internal version. So now we're going to do that conversion first. So from the input version to the internal version. And for this conversion, there were 3 steps. One was serialization. So from data to the Golang, so like a YAML or a JSON data to the Golang type. And then the second step was defaulting and conversion. So all of this is called decoding. Serialization. For that, you need to know which data you have. So like, do you have a YAML data? Do you have a JSON data? So all of this output media type, which media type are we looking at, YAML or JSON, is also derived from the request using the negotiated serializer or negotiate output media type method in this way. Next, we want to perform decoding. For that, we need a decoder. So this decoder is also created using the serializer, using the decoder to version method. So what does this do? It serializes, it does defaulting, and it does converting. We'll see that a little later. But to serialize something, you need something to serialize. So limited read body basically reads the request body. It just does a read all method on it. So it's not something fancy, it's just a simple read all on the request body. So you get the data. Finally, you do decode the data. So you also do defaulting and conversion with this. Decoding is done by the simple method called decoder.decode. That's literally it. After decoding, we have the internal version. Now we're going to do a few more things on the internal version. That is, first we talked about admission. So we had mutating webhooks and validating webhooks. So in this case, mutating admission.admit, the mutating webhooks are applied. And in this request func, the validating webhooks are applied. So we'll just quickly see what request func means. So request func calls r.create. It basically means that it's trying to create the resource. But it also passes this thing called admission to validate object func, which in turn calls validating admission.validate. So it's calling the validating webhooks and then it creates the object. Now we also learned that the next step after admission was doing some more operations on the resource before storing it. So let's see where that happens. So that happens in this directory called registry. So registry is basically a directory, and it's also a Golang type, but then we will not go too much into that right now. So there's this directory called registry, and it prepares the object for storage and does some validations on it too. So let's look at it. Since we're looking at creation, it also has this create method. So we'll just look at the create method for now. In the create method, there's this thing called before create. It prepares the object for creation by removing things like status part of the resource or doing some more mutations if needed. Finally, we're going to validate it. So we validate the object before storing it to etcd. And that's the main parts, the main function of the registry. Now we want to finally store it to etcd. So we have to convert it to the storage version. So let's see where and how that's done. So there's this directory called etcd3 because you want to store it in etcd. So let's see how that works. There is also a very convenient create method here. So we'll just look at that. And there we have this thing called runtime.encode. So previously we looked at the decode method. Now we are looking at encode. So we are deserializing it back to bytes. So we convert it to the storage version. All of this happens under the hood. So it converts to the storage versions and encode it back to bytes. And finally, that's done. So we call the etcd client and then store the object and put it in etcd. So that's kind of it for the code tour. Now let's go back to the slides for a bit. So we looked at the code base walkthrough right now. And let's very quickly touch base on this. To be very clear, I'm not going to be covering this in detail. So you might have noticed that we did not discuss about CRDs at all. CRDs and aggregated API servers are not part of the generic Kubernetes API server. They are aggregated with it, like the name suggests, but they're not part of the Kubernetes API server directly. They follow the same pattern though, so once you understand this, you can also understand the CRD and the aggregated API server code. But one thing I will call out is that the code for CRDs is stored in the directory called API extensions API server, and for aggregated API servers in a directory called kube aggregator. But covering them in detail deserves its own talk, so we will not be talking about them in this session. And that's kind of it for now. Thanks so much for attending, even though this is virtual. We have a feedback link, so if you have some constructive feedback that you would like to share with us, please do leave a message there. And yeah, thanks for attending. Be safe. Bye-bye.